PUNCH is a polarimeter. We are a collection of 4 cameras working as one virtual instrument spread out around the Earth. The polarization is something we're working on to do 3D imaging of our environment in space. So I want to set the stage here. Because we're doing space work, it's easy to think that what we're looking at is far away and will never affect you. That's not the case. We study the heliosphere, the environment around us, and that fits in with distances that are familiar. So right now, here in this room, we are 8 miles from the Riverwalk. You could walk that in a couple of hours if you really wanted to. Moving farther out, 800 miles, okay, is about as far as you can drive in a day. That's the size of the great state of Texas here. Let's put that in the context of the system we're looking at, the sun itself. So if we place Texas on a time-lapse movie of the sun, you can actually see how sunlight is produced. This is hot material boiling up from or rising up from the interior of the star, glowing, setting off sunlight, going out into space, and sinking down below. This is a time lapse, but it takes about 5 minutes for that to happen, for one of these bubbles called granules to rise, spread out and sink, and they're about the size of Texas. So it's a very energetic process, and that should bring this home to you. Well, Texas is large, but it's small compared to a star. So if we compare it even to the planet, that's 8,000 miles across, right? So 8,000 miles is you know, somebody who doesn't fly that often might fly that in a year. You probably drive that in about 6 months if you commute. But you can see that there's a lot going on this scale of the Earth. Let's put the Earth more in context. That dark thing next to it was called a sunspot, still is called that. It's a magnetized region where the surface of the star has a strong magnetic field that prevents that material from turning over. It looks dark because the new bubbles can't come up from below to glow. However, in the atmosphere of the star above it, it's much hotter. So sunspots are what give rise to what we call space weather, the auroras here on the Earth. If we go even farther out, we're now 800,000 miles. That's about as far as a long-distance trucker might drive in 10 or 15 years, or an airline pilot might fly in 2 to 3 years. So these are human distances, even though they're very large and astronomical in context. Moving out, I hope many of you saw the eclipse here a couple of years ago. Every once in a while, the moon goes in front of the sun, and we can see the atmosphere of a star. So if you saw that eclipse, you saw with your own eyes the hottest material you will likely ever see. That's 1 to 2 million degrees Celsius. The other thing that I like to point out is if you've seen that, you have seen electrons, right? Here in this room, we're surrounded by electrical equipment. We use it every day. We heard a talk about data centers and how we're harnessing electrons. What do they look like? Well, they look like that, right? That is what free electrons in space look like as they're scattering sunlight. The corona of the sun looks spiky like that because of the star's magnetic field. Also because it's so hot that the material is not confined to the star. It's sweeping out into space at 1 to 4 million miles an hour, all the time in all directions. And we are bathed in it. So this is 8 million miles across. That's as far as you know, somebody who's in United's 1K club goes in a lifetime of flying. But it's still a human distance. We can recognize 8 million miles. We have to stretch a little bit, but it's a human distance. If we go a little bit farther to 24 million, 3 times that, we're now looking at a field of view that's about the size of the constellation Orion. And we've subtracted a lot of glare here from the sun. This is a time lapse taken from space. You can see the stars moving past the sun as we orbit the sun. And this material coming out in all directions, tremendous clouds of stuff, both large and small, streaming out. Those large clouds are called coronal mass ejections, and they are the cause of space weather. They're important to power grids, to people who operate satellites. On the way down here, I was talking to a pilot who was sitting next to me who had to divert around the poles from time to time because of radio blackouts caused by these kinds of effects. If we move out even farther, this is the punch field of view now. And I'm going to come back to this in a moment, but I just want you to gather how large a field we're looking at. This is a 90-degree field of view, 180 million miles across. Now, it's hard to grasp that. If you were traveling at orbital speeds, orbiting the Earth, orbital debris, you would go from here to over the Riverwalk in 2 seconds. 2 seconds, 1, 2. Okay, it would take you 6 months at that speed to cross this field of view. Okay, so again, you can just grasp the size of this. And this stuff is right near us now. So PUNCH is examining this field of view in the inner solar system. We'll come back to it in a moment. What is PUNCH? Well, we built 4 spacecraft right here on campus in Southwest Research San Antonio. These are the imagers. We have a narrow field imager, also called NIFI. The spacecraft are about this long, so they're very small. We have 3 wide field imagers called WIFIs. The WIFIs, there are 3 of them because with a field of view this large, if you're close to the Earth, you discover that there's a planet in the way and you can't see what you're looking at. So we had to spread them out around the planet so we could look in all directions at the same time. This is what that looks like. This is a simulation pre-launch showing how the fields of view of the 4 spacecraft fit together. We're synchronizing them within 1 second of each other, even though they're spread out. We take 1 set of polarized images every 4 minutes, all 4 of them around the clock. They're doing it right now. We collect this full circular field of view every 32 minutes. In order to make these work together, we have to carry out extremely precise calibration. That's not complete yet. We're still working on it. That's why these images seem to flicker a little bit when I show them. These are some baby pictures as the spacecraft were being developed. This is the wide field imager, and you can see there's a deep baffling system there. And the reason for that is so that although this thing is sitting in the eternal noontime of space, that lens that you're seeing at the upper right is in a place that's darker. It's 100 times darker than the darkest night you've ever experienced. So it's an incredible feat of engineering that we're able to cast such a deep shadow in such a small space. Here's a picture of the clean room over in building 299 with a technician next to it, and that's the space, or in the clean room, that's the spacecraft there. If we turn it around, this is a picture of the team taken by the spacecraft. That's important because this is not a telescope we're talking about. This is a camera that's imaging our environment in space. And so here its environment happened to be the clean room before launch. This is vibration testing. This is thermal vacuum testing, just making sure that the spacecraft will survive. This is a large fraction of the team in front of the 4 crates just before we shipped off to Vandenberg. This is last February. In late February, we had unpacked the 4 spacecraft into a clean room at Vandenberg Space Force Base in California. And there's a technician in the background there, hard to get the scale. We bolted them to an adapter to go on a Falcon 9 spacecraft. Those are 2 of the WIFIs right there. There's NIFI on the right. And we went with SwRI, a different mission which had some Southwest components, actually, that deployed off the same rocket. That's a picture of the whole affair encapsulated crossing Vandenberg. It's a very rare picture because you can't take pictures on Vandenberg. But a passenger on an Amtrak train took that through the window as we were on our way to the pad. A couple of days later, 45 minutes after launch in California, we were over Madagascar and deployed from the rocket on little spring-loaded ejectors. So these are moving at a walking pace relative to that initial orbit. And in 120 days, they got out 120 degrees apart. And then we got this. So this is the entire inner solar system imaged by PUNCH. And I want to call out some of the things here because if you take one thing away from this talk, take away a sense of place. This is where we live in the cosmos. Astrophysics at home. So that's the sun there. This is a 90-degree field of view. You can see right here, that's Mercury and Mars, these 2 planets. That's Venus there. That's the moon. It photobombs us once a month. And this is a comet, Comet Lemon, streaking through. And the star of the show, what we're really here to look at, is these clouds of material that are coming out of the sun. Now, don't get me wrong, those are going incredibly fast. They look like they're just sort of billowing out, but they're streaking across our environment at up to 4 million miles per hour. They sweep over us. Some of them actually hit the Earth. Now, as this comes through, watch this comet, and you'll see one of these clouds goes out sideways, the CME, and it impacts the comet, and the entire cometary tail gets diverted by the motion. Here it comes. Boom. Right? So it looks small in this image, but remember, this is 90 degrees of sky you're looking at. So in order to make these movies, we have the most sophisticated data pipeline that's ever been made for a NASA science mission. 140 data products and counting just to make these mosaics work. We're still refining the data processing, but in the meantime, we can make these movies and show you this is happening all the time. This is the noontime sky you're looking at, with all the various backgrounds and sky brightness removed. Some bonus science we got. It turns out we're really good at seeing comets. And so we saw 3 of them this fall. This is at the top there, that's Comet Swan, which was discovered on September 11th this year. It turned out we'd been tracking it since August. We just didn't know it yet. And then underneath it, I chose this particular clip because this track underneath here, if you watch closely, has a faint dot moving from left to right, and it'll come around again. Look on the left with your eyes and you'll pick it up. That's Comet Atlas. That's an interstellar visitor. That's a rock that is visiting us and just passing by. And then down at the lower left is, that's a close-up of the Comet Lemon that you saw earlier where the tail was being disrupted. We can use that to probe turbulence in this medium. You think if space is empty, it's not. The solar wind is a turbulent medium, very much like winds here on Earth. So in conclusion, PUNCH is working. I wanted to close with this polarized movie just to show that we are starting to use the polarization signal. We've encoded the polarization of light as color here. And what you need to see is that although the stars are gray because they're not very polarized, the corona itself is brightly colored, and that's because it is polarized. The hue is telling you the direction, and the saturation of the color is telling you the strength of polarization. The 4 spacecraft are working great. We've downloaded 1.3 million images and counting. We're just getting started on the polarimetry. We have a website, and we expect more great things over the next year. So thanks.
Okay, we have time for a couple of questions. Have any? You may have, oh, here we have one.
That's great science. Do you expect the data to be used soon for space weather purposes or forecasting space weather on Earth?
Do you expect the data to be used soon to forecast space weather on Earth?
Absolutely, we do. We are currently shipping data to NOAA on a provisional basis so that they can evaluate PUNCH data for forecasting. We don't have a latency requirement on this mission, but we do happen to produce data with a low enough latency that it's useful for forecasting. So, yes.
I have time for one more question. Think you might have answered everything, Craig.
Oh, we got one in the back here.
Way back. Okay, yeah, we have one in the way back.
I'm curious as to what kind of upgrades can you make to these satellites from terrestrial as they are up there?
What kind of upgrades can you make to these satellites once they've been up there a while?
So we right now are using a single observing campaign. It's very important that they all work together and synchronously and in a steady way. But once the primary mission is over, we may consider trying to shake out and see how fast the camera will go and things of that nature. Of course, it's hard to modify the hardware, but there are a lot of things we can do with how we operate the hardware in the extended mission.
Thank you, Craig.
Thank you.